In this lab, we'll talk about converting circuit schematics to a physical circuit using a solderless breadboard and applying constant voltages using the analog discovery. Designing, analyzing, and building an electrical circuit usually begins with what is called a circuit schematic. A schematic is a stylized representation of an actual physical system. This is a schematic of our circuit. A schematic is a road map that describes the physical system. It shows the components, how they're interconnected, and it defines important variables and their sign conventions. Usually, variables and sign conventions used in analysis are also defined on the circuit schematic. We're just concerned with building this circuit, so I don't need to define any variables. The circuit contains three elements: a 5-volt voltage source that provides power, a resistor to limit the current, and an LED that lights up when current passes through it. Generally speaking, resistors are used to control current flow or provide a desired voltage difference. This is the circuit symbol for a resistor. This is what the resistors we'll use in our circuit look like. They have two terminals, and it doesn't matter how these terminals are oriented. You can swap them end for end without affecting the resistor behavior. The resistors have a set of colored bands on them. These bands provide a code that gives the resistance value of the resistor. I'll talk about reading color codes later. The 100 ohm resistor we'll use in this lab has bands that are colored brown, black, brown. This is the circuit symbol for a lighting emitting diode, or LED. This is a picture of the LED itself. The LEDs light up when you flow current through them, but the current has to be flowing in the correct direction, into the anode and out of the cathode. This means that LEDs are polarized or directional, so when building a circuit you have to insert them correctly into the breadboard, and you need to be able to identify the anode and the cathode. We'll use the lengths of the LED wires to identify the anode and cathode. The anode has a longer wire than the cathode. The next step in converting a schematic to a physical circuit is to identify the circuit nodes on the schematic. Nodes are simply points on the schematic where two or more elements are interconnected. However, wires, or perfect conductors, don't really count as circuit elements since they don't introduce any voltage differences in the circuit. In more official terms, a node is defined as a point that has a single unique voltage. There are no voltage differences inside a node. Since perfect conductors don't introduce voltage differences, we can put them inside nodes. Identifying nodes is a fundamental step in being able to assemble a circuit from a schematic. We identify nodes in the schematic and the breadboard, and then connect the components in the schematic to the corresponding nodes on the breadboard. These are the nodes I've identified in this circuit. The letters I've assigned to them are arbitrary. Node A connects the positive terminal of the 5-volt source to one of the terminals of the resistor. Node B connects the other terminal of the resistor to the anode of the LED. And node C connects the cathode of the LED to the negative terminal of the 5-volt source. Now we need to identify where the nodes on our schematic will be on the breadboard. To do this, we need to understand how the holes in a breadboard are connected. A typical breadboard is a large white plastic component with rows of holes in it. Each row will consist of 5 or 6 holes, which are electrically connected. Each row is electrically isolated from any other row of holes on the breadboard. Breadboards generally have one or more channels on them. The rows on either side of the channel will be isolated from one another. Since there's no voltage difference between the holes in a single row, each row of holes on the breadboard can constitute a node in a circuit. Exceptions are columns of holes that have a red or a blue line next to them. Now let's take a look at these concepts in the context of a real breadboard. This is a typical small breadboard. These 5 holes are electrically connected to one another, as are these 5 holes and these 5 holes. Any 2 rows are isolated from one another. This includes the rows of holes on either side of this central channel. So this row of holes is electrically isolated from the row of holes directly across the channel from it. The terminals of electrical components, for example this resistor, can be easily pushed into the breadboard holes. This allows us to use the breadboard to quickly interconnect circuit elements in order to create electrical circuits. For example, if I want to connect a second resistor to this terminal of the first resistor, I simply insert a terminal of the second resistor into any hole in the same row as the terminal I want to connect it to. Now, these two terminals are connected. These two terminals are isolated from one another. If it's convenient, I can use jumper wires, just pieces of wire that have the right diameter to fit into a breadboard hole, to directly connect two rows of holes. For example, if I place a jumper wire between these two rows, both rows are now electrically connected and they constitute a single circuit node. Many breadboards will have what are called bus strips running along the entire length of the breadboard. Each bus strip will generally have either a blue or a red line next to it. All of the holes in each bus strip are electrically connected. These strips can make it easy to connect the same voltage to multiple nodes. This is used mostly in larger circuits. Now let's use a breadboard to implement this circuit. To do this, we just need to assign rows of holes on the breadboard corresponding to the nodes on our circuit. Then we insert the terminals of our components into the holes on the breadboard that correspond to the nodes that the component terminals interconnect. I'm arbitrarily selecting this row of holes as node A, this as node B, and this row of holes as node C. Now, node A connects the positive terminal of the 5-volt source to one of the terminals of the resistor. Node B connects the other resistor terminal to the anode of the LED. And node C connects the cathode of the LED to the negative terminal of the 5-volt source. Our resistor has a resistance of 100 ohms. Its color bands are brown, black, brown, gold. We'll connect the LED's anode to the resistor. Remember that the anode is the longer of the diode's terminals. By plugging the anode into a hole in the breadboard that's in the same row as one of the terminals of the resistor. Now if we're using V+ to apply our positive voltage, we plug the red wire into a hole in the breadboard that's in the same row as one of the resistor's terminals. I'll use this connector to make a male-to-male connection. Then I plug a black wire into the same row as the diode's cathode. Now all we need to do is use the waveform software to turn on power to the circuit. To apply voltage, click on the supplies icon on the waveform's welcome window. We only need the positive supply, so I'll turn the negative supply off. The positive supply is indicated as being ready. I'll set the supply voltage to 5 volts. Clicking on the Master Enable button now turns on V+. Power is applied to the circuit and the LED lights up.